Okay, so in this video we're going to talk about gravitational potential energy, and hopefully that sounds familiar, but it means a little bit something different now that we have established a force due to gravity. Okay, because the potential energy that we're used to was used when we were calculating the energy when we were relatively close to the surface. Okay, and we kind of addressed this earlier. The idea is that even if you were standing on a mountaintop, if we zoom out far enough to be able to see the curvature of the Earth, we wouldn't be able to see the top of that mountain. So even at the top of a mountain, you're still pretty much on the surface of the planet. Okay, so for this idea of gravitational potential energy, we're trying to look at situations where we are well beyond the surface of the planet. So quickly, a little review on potential energy. Remember, potential energy, the change of potential energy is equivalent to the negative amount of work done by a conservative force. Okay, and remember the work done was an integral of the force over some applied displacement. Okay, so we're going to use this expression to identify what gravitational potential energy becomes when you're far from the surface. So again, if I take this planet, say this is Earth, and we have an object that's near the surface, we know the potential energy was given to us by mass times gravity times the vertical displacement. Right? However high you were off the ground determined how much gravitational potential energy you had. Okay, but now what we want to do is we want to put an object that's much further away from the surface. Okay, and so one of the ideas we look at is when we calculate the potential energy, we need to have two positions. Because remember, potential energy is only relevant if we know the difference in two locations. So one of the things that helps us is that we want to move this object to a point where we know there will be no potential energy. It's good to pick a point where we know the potential energy drops off. Okay, so because of Newton's law of gravity, and you can check this by the formula, there is no value that you could put in the denominator of that equation that would make the whole thing equal to 0, unless you put in a very large number like infinity. So the idea is we start this object some distance from the surface of the planet, and then we want to move it out from there to a place infinitely far away so that the potential energy disappears. Okay, and so that's our setup. And with this, we're going to develop a new form for gravitational potential energy. So if we use the general equation for potential energy as the negative work done, okay, the force times the displacement, well, the force is the gravitational force. So it's the gravitational constant times the product of the two masses divided by the distance between them squared. Okay, and the distance is along the radial line, so that's why we're going to keep it as dr. Alright, so if we do the math, so we see that the constant and the two masses come out, and again, when you look at the limits, we're starting at a position r from the center, and we're jumping out to infinity. Okay, so we're going to take this expression and simply find some solution to tell us the potential energy due to gravity when we're far from the surface of the planet. So the antiderivative of 1 over r squared becomes negative 1 over r. Okay, I'll let you guys work that one out. And then we plug in our limits. So remember, it's the upper limit minus when I plug in the lower limit. Okay, now from here, 1 over infinity is practically 0. Right? 1 over a very large number is essentially 0, so that term disappears. Okay, and then the two negatives make a positive 1 over r, so we get a final expression of negative gravitational constant times the product of the masses divided by the distance between their centers. So this becomes our expression for the gravitational potential energy. Okay, and so now that we have an expression for potential energy when you're far from the surface, we can now use conservation of energy to figure out the motion of things as they're moving towards or away or from a planet. One of the applications of that is to understand what you need to do in order to get, like, say, a rocket away from the gravitational effects of a planet. Okay, so let's do that example real quick. So one of the things this is referred to is it's called the escape velocity. Okay, it means that if you've got a planet and we know the mass of the planet and some properties of the planet, if we need to get some object off the planet and move to a point where the planet no longer has gravitational influence, that is referred to as the escape velocity. So let's imagine the Earth, and we've got a little rocket up here at the top, and we're trying to launch it away from the planet, and we're trying to reach a point so that we lose all gravitational effect and we've escaped the Earth's gravitational pull. Okay, so that basically gives us the definition for the escape velocity. It's the minimal amount of speed that's required in order to escape the gravitational influence of the planet. Okay, so to do this, we're going to use conservation of energy. So you remember conservation of energy, it's the sum of the kinetic and potentials, both before and after. Okay, now when we do this, the important thing is to understand what's going on the after side. Because if we're moving out far enough for gravity to lose influence, that means the potential energy is disappearing. And it also means that we've reached a point where gravity has slowed us down all the way until we've stopped moving. But the instant we stopped, we got just outside of gravity's pull. So that's why the kinetic energy is zero. Because again, we've reached the point where gravity causes us to stop, but we're too far away for gravity to pull us back in. Okay, and then the potential energy, this kind of went the way we developed it. In order to get that far, where we lose potential energy, we go all the way out until the point where R is essentially an infinite distance away. Okay, so you could plug in R to infinity for that function, and it'll become 0. So all we have is 1/2 mv squared, and that v becomes our escape velocity, plus the negative of gravitational constant times the product of the masses over the distance squared. So if we solve this for the escape velocity, we move the potential energy term to the other side. The mass of the rocket cancels. We get rid of the half by multiplying 2, and then we take the square root. And so we find an expression that says the escape velocity is equal to twice the gravitational constant times the mass of the planet divided by the radius of the planet squared. Now, I didn't really show that in the problem, but the point is the rocket starts when it's on the surface of the planet. That's where it takes off from. So the r that we were using in these equations is really the radius of the planet itself. Okay, so this number is important because it represents a minimal limit, that if you don't launch with at least this much speed, you'll go too slow, and by the time gravity stops you, you're still in gravity's pull. So it'll take you back down to the planet. Okay, if you launch with a velocity greater than this number, then you'll be moving outside of the gravitational pull with no problem and still have some speed to keep going.